So this is chapter 2 of Nocedal and Wright, numerical optimization. Let me write that in case people come in and don't know what we're doing here. Chapter 2 from Nocedal and Wright, numerical optimization. Okay, so this chapter is called Fundamentals of Unconstrained Optimization. So here we have it unconstrained, and so this is a much simpler case than what we'll usually face in chemical engineering or control. But the basic structure is that when you have an unconstrained optimization problem, you want to do something like minimize some function, and you just say there's no constraints, like just find me the value of the decision variables that makes this as small as possible, and you don't impose additional constraints. And then so in this, the notation being used is that x contained in r to the n is a real vector. And it has n components where n is greater than or equal to 1. So that means you have n decision variables here, where each of these xi's is a decision variable. And the function f itself, even though it takes a vector, it maps it to a scalar. And we're going to assume that this is a smooth function so that you can differentiate it. So what happens with optimization then is that if you just ask this question, find the minimum of this function by changing the decision variables until you find the one that makes the function as small as possible. In some sense, you can think of that would be a very brute force search. You would have to test every value of f at all the different values of x, and then see which one of those gives you the smallest possible value. But algorithms don't work like that in general. They don't test every single point. They try to find ways of reducing the search space that they have to search. And one of the things that they often use is things like derivatives and stuff like that. And so what we're going to be doing in this chapter is going over some of the theory. We won't cover all of chapter 2. I'll cover maybe about the first half or so. But this will be a theoretical type lecture of some of the theory that underpins optimization. And so to look at an example of what might an unconstrained optimization problem be, and to start to think about what are some of the challenges that you might face when you have an unconstrained optimization problem, we can look at this example. So here is a problem statement. So say we want to fit a curve to experimental data. So that means that we'll say that we have our measurements. So these are in some sense a dependent variable. So we'll have many of them, y1, y2, ... ym. And we'll also have our independent variables. So let's just say that that's time. So here's what changes is the time changes, and then the measurements change as time changes. So we have t1, t2, ... tm. We have m data points. Maybe it's something like this, like time and y. We have some different data points over time or something. So pretend that someone already said, I think that a good function for fitting this data might look something like this. So it might be some type of function of p and then some parameters x. So these are our decision variables. We don't know these. These are parameters. Parameters of the model. And this is what we want to fit. So it's equal to some constant, which here is x1, but remember, we're not talking control here, so this is not a state. This is actually the decision variable. It's actually one of the parameters. This might look more familiar to us as something like C1, but here we're using x to represent decision variables, so that's why it says x1. x2 e to the negative x3 minus t squared over x4 plus x5 cosine of x6. So we'll say that we have this. Let's pretend that someone already told you, you think this model, if you fit these parameters good, will do a good job of fitting whatever data you have. I don't know that it looks like this. Okay, some data. And so the first question you might be wondering is, how did they come up with that model? Well, that's not the question of optimization. That's already a question in the modeling of the optimization problem. So someone is telling you, I think this will fit it. If you want to talk about why you think that, then you can like look at whatever data there really is, and you can try to guess. Maybe it looks like sort of has like an exponential way of acting and sort of has an oscillatory way of acting and those different types of things. But that's not the problem that we're considering here. Not where did this function come from, assuming someone told me this is a good function. What are the values of x1, x2, x3, x4, x5, and x6 that cause this to fit my data as closely as possible? So we want phi of px to fit the data as closely as possible by selecting good x's. And so we can call our decision variable vector as being x1 to x6. And what we'll do is to define this problem mathematically, because we always have to define what we want to achieve mathematically in optimization to set up an objective function. We're going to define a difference between our observed data and each of the data points. And so what this is going to look like is it's going to look like a residual rj of x is equal to yj minus phi of pj and x. And we have j is 1, 2, ... m. So this means that we'll have a residual for every one of our m data points, and that each time we will keep the same values of our decision variables, so the parameters of the model, but the t's are different every time and the y's are different every time, and we get the difference between those. So then we can say, okay, my goal, if I go back to it, my goal here is that we want to fit the data as closely as possible by selecting good x's. So what we want is for all of our residuals to be as small as possible. So one way of trying to do that is to minimize the sum of all the residuals. So here it would say x and r to the 6, because remember, x here is our decision variables, and we have 6 of them here, x1, x2, x3, x4, x5, x6. So minimize over all of these numbers. F of x, where this is now our objective function, is equal to, and we'll say residual 1 squared of x plus residual 2 squared of x plus ... plus residual m squared of x. So a few key things to note here. One of them is that this looks kind of easy compared to what we usually do. But that can be a little deceptive, even in terms of computation time. So this looks like, well, how long can it take to figure out what's the minimum for that, right? I mean, you just have to calculate this one objective. Isn't that pretty easy? Well, you can see that if m gets really large, what I'll call the number of arithmetic operations becomes large also. It becomes larger. So the reason that's significant is that even though this is not even constrained, right, but just computing this objective function on its own could take the computer a little bit of time if you have tons and tons of data points. Like if you had 1,000,000 data points, then just to compute like this function 1,000,000 times, even for a fixed value of x, could be take a little time. So that's one of the things. And you can also see that there's probably for most of the data points going to be some residual, because just this model, right? I mean, if this is not exactly how the underlying dynamics are described, then you will probably have some error at many of the points. And so you would not expect your objective function in the end to evaluate to a straight up 0, even if you choose the best x's, just because the model itself is not capable of fully representing the underlying system 100%. And then so the next question that comes up would be, like, how do I know when I get back something? So say that it gives me an x when I solve it. So solving gives me an x that gives f of x is equal to 0.34. So now the question is that really the solution? So is that really a minimizer of f of x? It becomes non-obvious at that point because it's clearly not 0, and we know that the minimum of this is at 0. So when it gives me some other number, how do I know, or how do I feel confident that I really found a minimum? And so what we need to do then is we need to do two things. So one is define what solutions are an optimization problem. We need to define what allows me to say this is a minimizer or solution of the optimization problem when we're solving it algorithmically, and even when we're not. That's why this is a theory lecture, is that it's just putting theory forward. And we also need to say what are the characteristics of solutions so that I can be sure I've got one. And remember, we're only talking about unconstrained minimization. So even though we can define solutions, in general, a lot of the things that we'll say will be true with constraints, but then you'll add like, plus the constraints are satisfied. And then characteristics of solutions, actually there will be more conditions. So we're only looking right now at unconstrained optimization. That's an important distinction so that later when we add more conditions or more components, that then you're able to say, oh, right, even though we did some before, there's more to it when you add constraints. So that's where we're at. Now we're going to talk about the first thing is definitions of solutions to optimization problems. Always important to define what you're trying to achieve mathematically. So defining solution. So there's a lot of different terms. And so one of them is the term global minimizer. So here's the formal definition of global minimizer. So a point x star is a global minimizer oh, sorry, it says if f of x star is less than or equal to f of x for all values of x contained in R to the n, or the domain you care about. Right now, since we're considering it's unconstrained, it should be over all of R to the n, but if you're if you don't actually care, as the person designing the optimization problem, if there's a smaller point, say for example, that it's like, oh, well, the following design minimizes my cost, but the temperature would be 1000 Kelvin. Maybe you're like, okay, like I didn't put any constraints on this because I didn't like want to complicate my problem, but I really don't care if there's a smaller value at 10,000 Kelvin, something like that. So this says that like your global minimizer technically, if it's unconstrained, is like this, but you may have cases where you model something as being unconstrained just to get the easiness of working with it that way, even if it is constrained, and then maybe you just don't care about certain parts of the domain. And so if solutions come back saying, well, something over there is better, you're just like, whatever. So, okay. So it can be hard to get a global minimizer in general of any function, because that would mean that somehow you have knowledge that there is nothing else in any other part of like an entire set of real numbers that makes your objective function smaller than the current value that you have. So it's hard to find that because that implies some type of like global knowledge of the function's way it behaves. And so when you design an algorithm, of course, you could achieve that if it really tests every single point, like with a brute force search, but that would be very time consuming. And so generally, when we have algorithms, we don't go test every single point to get global knowledge. Generally, we only test some points, and then we check nearby points. Is there anything better? And we get a local solution to an optimization problem. And so most of the time, we will be working with local optimizers. Things like IPOpt and fmincon are local optimization solvers. If you really needed a global one, then we'll have to look at other things. But so a local minimizer is defined like this. So a point x star is a local minimizer. If there is a neighborhood which they write it as n, of x star, such that f of x star is less than or equal to f of x for all x contained in n. So here's the definition of a local minimizer, and we can compare it to global. And we can say this one just requires there to be a neighborhood of x star such that you have a lower value for all points in the neighborhood of your objective function evaluated at the local minimizer compared to evaluated at all the other points in the neighborhood. So then you might say, what's a neighborhood? So a neighborhood of x star is an open set that contains x star. So when we talk about an open set, around, like generally here, an n-dimensional vector. So there we go. There's a difference, though. You can actually refer to minimizers as either strict or weak local minimizers. So if it's like this, this will be a weak local minimizer. If this is going to be f of x star is less than f of x, that would be a strict local minimizer. Or a strong local minimizer. Strict local minimizer, sorry, or strong local minimizer. Sorry about that, it's a little messy there. That for x is not x star. Of course, it won't be strictly less at the, like you wouldn't have f of x star is strictly less than f of x star. It can, those will be equal. Okay, so now we can define two more things. Or actually, there might only be one. So here's another point. So a point x star is an isolated local minimizer if there is a neighborhood n of x star such that x star, oh, it says x, x star is the only local minimizer in N. So at first, and this is something that we looked at a few years ago, and we were like, I don't understand how something could be a not isolated be not isolated. So I think what we saw was there was some interesting cases where there was a function that was like this or something, so that like no matter what neighborhood you went to, there was always somehow a local minimizer near it or something like this. And the reason that came is because the book says some strict local minimizers are not isolated. And we were like, whoa, what the heck? How could that be true that there is something that has f of x star is less than f of x, but it's not isolated? And so then we looked up and we saw a function that was doing something like this, where it just was oscillating so much that then I guess it meets the definition that there's a neighborhood such that the minimum point is less than all the other points, but that somehow it's not the only one. It's fine to ask a question as long as you don't mind it being recorded. If you don't, go ahead.
I guess like it's I know this is probably exactly what you're trying to explain, but I don't understand why you can go to strict local minimizer and the only difference is that it's for x that are not x star. So that means you're no longer restricted to the neighborhood when you're a strict local minimizer. I'm trying to figure out what's the difference there.
You mean between the weak and the strict? Or between the isolated and the strict?
Between the weak and the strict.
Ah, okay. That's a good point. Yeah, so the difference is if this is an equality or an inequality or like a strict less than. So this one says that for all the points that are in the neighborhood, that then F evaluated at your like a weak local minimizer has to be less than or equal to the F at any other point in the neighborhood. But here, F evaluated at the minimizer has to be strictly less than any other point in the neighborhood. So I think there is an example in the book, so I can use this one. So it says like F of X is equal to 2. It says every X is a weak local minimizer. Because every X gives the same value of the objective function. And so they're all equally small, but in any neighborhood you take around a given point, so say I take this one, I look at the neighborhood around it, all of these around it also have that F of all those X's is equal to 2. And so f of any x is less than or equal to, so f at any of these x's is less than or equal to f at all the other x's. It's actually equal. So this one is only a weak local minimizer because there are many points here that have the same value of f of x. But then if you look at this other one, so here f of x is equal to x minus 2 to the fourth. This one will look however it looks, which I believe will be something like, this will have to be something like maybe x is 2, I guess. So here we have, so the axis is somewhere over here. But here it has a strict local minimizer, so there's only one point when x is 2 that this is as small as it can be, and that any other point nearby, so for any other f of x that's not optimum, this is greater than strictly the one at f of x star, which is equal to 2. So there's no other points, which is different than, for example, if you have it go like this and then it's like flat and then it comes up again. Now all these points nearby have the same value of the objective function, including this one. And so all of them are weak local minimizers. Does that help?
Yeah, that helps. Thank you.
Yeah. And then the weird one is the strict one, though, because the strict one, I guess there's this function like f of x is equal to x to the fourth cosine of 1 over x plus 2x to the fourth with f of 0 is 0. And then, so this one, according to the book, it is twice continuously differentiable. It has a strict local minimizer. At x star is equal to 0. And then it also says that there are strict local minimizers at many nearby points. Xj. And it says they can label the points so that xj goes to 0 as j goes to infinity. This is at least what the book says. So I think I would have to look back at this function again. I think the way we looked at it was we looked at it before in Google. And so just by like typing in the Google like graphing function, and then we had to keep zooming in to figure out what was meant by this. There's some type of interesting behavior that this one has where I guess it has at x star is 0 is where compared to the nearby points in some neighborhood, there's a lower point. But then there are always many strict local minimizers at many nearby points. And so I guess it has some weird type of behavior. So that probably makes more sense for someone if they look up that function and try to see how these two things reconcile. I remember we did that a few years ago. And I think it like looked weird as you zoomed in or something like that, as you zoom in around 0. So there's the idea. Okay. So it says, so here's just one other point on this. So strict local minimizers are not always isolated. But all isolated minimizers, or sorry, isolated local minimizers are strict. So then the example in the book that they talk about next, then they just say very briefly, like, you know, it can be very hard to deal with problems when the objective function is really shaped kind of weird. So like maybe a very nonlinear function. And that when, for example, it says if you're trying to get molecular conformation that then the potential might have millions of local minima. And so this can be a challenge for actually doing some stuff like we would want to do in chemical engineering. And so it says sometimes maybe you have some additional global knowledge about your function, and that could help you maybe go toward the right place to search and try to help you find the answer. But in general, getting global minima is a challenging problem. So now that's sort of the theory of what are minimizers, how do we define that mathematically. Now we're going to do the part of the local minimum characteristics. So how do you know if something is a local minimum? It should meet the characteristics required. So we are able to use this information that we're going to talk about in developing algorithms that help us search when we have a differentiable objective function that help us to search for the minimum of that objective function more quickly. And so because of that, we have all these interesting characteristics which are used in like very, very strongly in algorithm development. And also proofs of what like that your algorithms will converge. So that would mean you will actually find some answer if you run the algorithm long enough, things like that. So this kind of theory is used for those kinds of things. So right now we are going to look at twice continuously differentiable functions. Objective functions. So these are functions where first derivative exists and is continuous, and so is the second. So there's several math things we just need to put out there. And the first one of these is Taylor's theorem. The book says this is in any calculus textbook. I'll be honest, I've never seen this. But actually, that might not be true. I haven't reviewed my multivariable calculus in a while, so maybe it is in there, at least from a single variable perspective. This does not look like a theorem I have seen exactly written this way, but this may be in a multivariable part of the textbook. If I look back, I'll see this written exactly this way. But suppose that f maps, here again, our objective function can take a vector valued input of all the decision variables, but it does have to give a scalar output because we're optimizing a scalar function, and it's continuously differentiable. And that there's some vector p also in R to the n, which is the same space as the decision variables. Then this function f evaluated at x plus p, where remember this is an R to the n vector, is equal to f of x plus the gradient of f at x plus tp transpose p for some p contained in 0 to 1 as 1. And it also says, moreover, if f is twice continuously differentiable, so here was just continuously differentiable, we're going to focus a bit more on twice continuously differentiable. So if f is twice continuously differentiable, we get more. What we get is that del of f of x plus p is equal to del f of x plus the integral from 0 to 1 of del squared f of x plus tp p dt, and that f of x plus p equal to f of x plus, f of x plus del f of x transpose p plus 1/2 of p transpose L squared f of x plus p for some p contained in 0 to 1. And again, you just sort of have to take this for granted that this is in a calculus book because they do not provide any proof in this book, and they say, and calculus book will tell you this. Oh, there you go. So this is twice continuously differentiable. So this one is, if f is continuously differentiable, then this is true. And they use this in the proofs, and we're going to use this in a proof in just a minute. Some t in 0 to 1. And then if it's if your objective function is twice continuously differentiable with respect to your decision variables, then here we go again, we have 2 new properties, and those are going to be used in proofs in just a minute. So if you're wondering what's the point of this, it's that if these hold true, we can prove stuff. And we are caring here about whether or not our objective functions are differentiable in setting these conditions. So now we're going to look at what we call necessary and sufficient conditions for optimality. In general, the concept of a condition being necessary means that it needs to hold for something else to be true. And the concept of something being sufficient in general means if that holds, then another conclusion is true. And so if something is both necessary and sufficient, it's like an if and only if, but you can sometimes you have it where it only goes one way. So now we're going to look at the conditions. Some of them are going to be necessary and some are going to be sufficient. So first, we're going to have necessary conditions for optimality. So the way that we're going to get these is we're going to say assume that x star is a local minimizer. So these are necessary conditions. Again, for optimality of unconstrained, oh, sorry, I didn't mean to cross that out. I meant to underline. Necessary conditions for optimality in unconstrained optimization. And so the way that we're going to do this is it's going to say, essentially, assume x star is a local minimizer. Then blank, which we're going to see about the gradient vector at x star, and Hessian, which is the second derivative matrix at x star. So this is how the necessary conditions are worded. They start by saying, if it is a local minimizer, then these things are true. That's why it's necessary, is that if it is a local minimizer, it is also necessary that these things hold. So here's what we call the first order necessary conditions. So this is going to be if x star is a local minimizer, and f is continuously differentiable. In an open neighborhood of x star, then del f of x star equals 0. So this says if you know your local minimizer is at x star, and you also know your objective function is here just continuously differentiable in an open neighborhood of x star, so around x star, values of your decision variables near that, very loosely, then if you take the gradient at x star of the objective function with respect to those decision variables, it should equal 0. So that is a true thing. And you can say, oh, how do I know that? So we're going to do a proof by contradiction. So here is the proof of it. You can prove that the first order necessary conditions hold. So we'll start by saying, suppose, this is proof by contradiction. So the way to start those is suppose that LF of x star does not equal 0. So then what we're trying to do is we're trying to show that if the conclusion is not true, then x star cannot be a local minimizer. So then define P is equal to negative del F of x star. And then you have that P transpose del F of x star equals negative of the norm of del F of x star squared. And this is negative because norms are always positive. So if there's a negative in front of it, that's this whole thing is to be negative. So far what we've done is here's a P. And so P transpose del F of x is going to be negative del F of x. So negative del F of x star transpose, if you transpose that, times the del F of x star. I should not have put the arrow that way. I should have put the arrow to this. There we go. Now that's corrected. And this is equal to negative del F of x star squared. Yeah, go ahead.
So I noticed that it says, like, then basically the gradient of x equals 0. So that means the first derivative of all with respect to every single variable is equal to 0.
Exactly.
I'm wondering, is it possible to have a minimum where one of the derivative of with respect to what at least one of the functions is, variables is not equal to 0? Is that possible?
It's a really good question. That's actually why these are the necessary conditions, is they say if it is a local minimizer and f is continuously differentiable, then this holds. So the answer is that if it's a local minimizer, no, you can't have anything except this. This is actually a necessary condition for any optimal point, that the gradient first derivative vector evaluated at the optimal point has to equal 0. And we're proving that that must be true right now. There can't be anything else. That's a really good question.
Okay, thank you.
Yeah. And the way we're proving this is we're taking a contradiction. So we're saying, what if it wasn't true? So exactly what you just said. You said, could it not be true? And then so that's actually how this proof starts, is it says, what if it isn't 100% 0? And then we say, okay, let's take that further and see what happens. So it starts by saying, we'll define just some vector. It's P, it's negative del F of x star. Let's just define that. And then we'll do P transpose del F of x star. So far, that might seem very unmotivated, like, so what? But yeah, I can do that. I can do P transpose del F of x star. And then it gives me this. And I know that that thing has to be negative, because the norm of any vector is going to be positive, and if it's squared, it's positive. So if there's a negative in front of it, it must be negative. And then we use the principle of continuity. So because the gradient of f is continuous, that's why this is a continuously differentiable function. So that's where we're using that statement, is continuous near x star. There exists some scalar t greater than 0 such that P transpose del F of x star plus PP is less than 0 for all t contained in 0 to t. So what this says is it says that because it's continuous, and I know that P transpose del f of x star is negative, if I take a sufficiently small enough point away from x star, because del f is continuous, I can't suddenly jump from this function being negative to it being positive if I get this P very small. I mean, if it's like minuscule, so that I'm still almost at x star, then because P transpose del f in that case, when I'm actually at x star is negative, then when I do P transpose del f evaluated at a point almost at x star, but only slightly off, because del f is continuous, this still needs to be negative. It can't have changed so drastically. That's the idea. And then what happens next is that for any P contained in 0 to t, then the Taylor's theorem, which we can look back at to see how this is related, gives us that f of x star, sorry, this always makes a stray mark, f of x star plus t bar p is less than f of x star for all p contained in, oops, this side should be open, 0 to t closed on the right. So this side is open, that side is closed. And so this is just saying like, okay, so first I said, let me try the case that del f of x star is not 0, and let's see what happens. Then I just said, I'm going to define a random vector. It's related to the del f of x star. It just, or sorry, not a random vector. Like I'm going to define this vector, and then I'm going to use it to make this what seems kind of unmotivated transpose del f of x star. The reason we use that is because we said, well, that's negative. That means if I look at it not too far away from the original point x star, it will also be negative. And then now we're going to use the Taylor's theorem. We're going to say, well, you know what? I can come back here and I can say, I'm looking at this part. I know this is negative for the point I was looking at because we had the P transpose del f of x plus TP was negative. So there exists some small t where this was going to be negative for me. And then I can say, well, that means that f at x plus p is less than f of x. Sorry. I didn't write the intermediate step that clarifies that. F of x star, this is the part that looks like Taylor's theorem, plus t bar p, this is what we were just looking at, is equal to f of x star plus t bar p transpose del f of x star. Oh, this thing making so many stray marks, plus tp for some p contained in 0 to t bar. And then that leads to this condition. So what we have here, this is the statement of the Taylor's theorem, if you want to compare. Here, x plus tp, here, x plus t bar p. So here, the t bar p is the role of the straight up p over here. And then we say it's equal to f of x star. That's the corollary of this part, f of x star. And then we say plus the t bar p transpose. So here, because the t bar p is playing the role of p, we t bar p transpose, and then del f of x star plus tp, and the t there is just without a bar, and that one has to be between 0 and t bar. So it's some fraction of allowing some fraction of this to be like the t bar p times some fraction. So then, because we know that this part is this, which is negative, that means that this is subtracting from f of x star, so that f of x star plus tp must be less than f of x star because it's equal to f of x star minus something. And so then what this means is that if this holds true, then there is some direction given by this like p bar p that is not at x star, where we actually see that f at this new point is less than f at the point I said was my minimizer. Therefore, it's not a minimizer. So this is the contradiction, and so it means that we must have the other thing, so that it cannot be true that del f of x star is not 0 at a minimum. It must be true the other way. So that is the proof here for the first order necessary condition for optimality, which, if you have to summarize it, is basically just if you have a continuously differentiable objective function and at the local minimum, the gradient vector is equal to 0. So that's first order necessary. But just because that's true does not mean it is a local minimizer. So if you find a point x star where this is true, so I guess let me say that again. If you frame it the other way, you'd say, I have a point, I don't know if it's a local minimizer, but del f of x star for that point, or del f of x for that point is equal to 0. Is it a minimizer? And the answer is you don't have enough information to tell. So it would be what we call a stationary point. So if del f of some point is equal to 0, then this point, x star, is a stationary point. But whether it is a local minimizer, you can't tell. You can't tell yet. But the other way around, if you know it is a local minimizer, then x star is a stationary point. So the first order necessary condition is necessary but not sufficient for optimality. So it's necessary that if you know it's a local minimizer, then it must be a stationary point. It must satisfy that the gradient is of f of x star is 0. But if you only know that the gradient of f of x star is 0, that is not sufficient for claiming that it must be a minimizer. There's more that has to hold. So necessary but not sufficient. So now, here's just a quick definition. So a linear algebra terminology, a matrix B is positive definite if P transpose BP is greater than 0 for all vectors P that are not 0. And we say, so this is positive definite and it is positive semi-definite if P transpose BP is greater than or equal to 0 for all P. This is a property of a matrix. And so the reason we define it in this weird way is that this, when you do P transpose B, so if we even just say that we have a matrix that I know is positive semi-definite, so 2, 0, 0, 5. Okay, here's a matrix that, or sorry, I know this one is positive definite. But so let's say I take any vector, and then that will be like, I don't know, 1, 3. Oh, I need to do the transpose. Sorry. 1, 3. And here we have 1, 3. So now we have to multiply these together and see whether or not this is positive or not, or equals 0 or not positive. And so you can do the multiplications here for this one, and it will be like whatever, 2 and 15, and you can multiply that together and it will give you 2 plus 45. So this is equal to 47. So you can see this one is greater than 0. To be positive definite, you would have to check this for every possible p that is not 0. And you would have to see that all of them are positive. Now, it turns out you can actually prove things in linear algebra, that there are ways easier than check every one of the points. Like you can check things about eigenvalues and stuff like that. But this just gives the feeling of what is this definition trying to tell you? It's trying to tell you that if a matrix is positive definite, that literally means you can take any p and you can do this type of multiplication with it, and then you always get back a positive number. It's a positive scalar, so these are scalar values. So now let's do second order necessary condition for optimality. So here we've got second order necessary conditions. For optimality. So because these are the second order necessary, it's going to be somehow related to what's necessary related to the second derivative. So this is going to say that if x star is a local minimizer of f and L squared f exists and is continuous in an open neighborhood, of x star, then del f of x star is equal to 0 and L squared f of x star is positive semi-definite. So this is again necessary. So it says the assumption is that x star is a local minimizer of f. And we're assuming not just continuous differentiability, we're assuming something stronger, that the second derivative, or the Hessian, the second derivative matrix called the Hessian, exists and is continuous with respect to the decision variables in an open neighborhood of x star. Then not only does x star need to be a stationary point, but also the second derivative matrix or Hessian has to be positive semi-definite. So these are things that must hold at a local minimizer. So if you see a point x star and one of these does not hold and del squared f exists and is continuous, then you say that point cannot be a local minimizer, because if it is a local minimizer, these things have to be true. Just because it doesn't go the other way. Just because these things are true, it does not say that that means it is a local minimizer. It's saying that if it is a local minimizer, these things must be true. So if they are not true, you can know it's not a local minimizer, but it doesn't say if they are true that for sure it's a local minimizer. It's necessary, not a sufficient condition. We can also prove this one though. So the first part of the proof is, of course, that del squared f exists and is continuous. That means that del f exists and is continuous. And we already proved that under those conditions, this part is true. So we already know that part. So we're good. Now we just need to prove this second part about the Hessian. We're going to do it the same way. We're going to make a contradiction, we're going to do proof by contradiction by saying, assume this part is not true, and then demonstrating that if this part is not true, x star cannot be a local minimizer. So we're going to do assume, here's the assumption that is what we're going to show is not right. So assume that del squared f of x star is not positive semi-definite. And we're going to show that this will not give me a local minimizer. We're going to do something very similar, where we're going to say, then choose p, some p, such that p transpose del squared f of x star p is less than 0. So how did I get this? This is related to semi-definiteness. So we're saying this is a matrix. If it is not positive semi-definite, it has to be the opposite of positive semi-definite, which if we look back and say, what is positive semi-definite? That means this is always some P transpose of your matrix times P is greater than or equal to 0 for all the P. So if we say it is not this, that means this has to be less than 0 for some P. So find some P where this is true, because that would be the definition of it not being positive semi-definite. So then we do a similar argument to what we did last time, where we say because L squared F is continuous near X star, there is a scalar P greater than 0, such that if we do P transpose del squared F of X star plus P, P gets less than 0 for all P contained in 0 to T. This is similar continuity argument, what we did related to the first derivative in the prior proof for the first order necessary condition. Here we're saying, okay, we know that del squared F of X star is not, or we're assuming it is not positive semi-definite in some open neighborhood of X star. So that means if this is negative and this is a continuous, and it's negative let me go back. It exists and is continuous in an open neighborhood of X star. We're assuming that it exists and is continuous in an open neighborhood of X star, but that it is not positive semi-definite there. But because it exists and is continuous, if it causes, if del squared F is not positive semi-definite at some point, then you go slightly off that point. Because this exists and is continuous, you should still have it so that this is still negative, or sorry, so that this is still negative for a small amount off the original point. So now what we need to say is to say that what does that do for us? So now we're going to look at a Taylor series expansion around X star. In a very small neighborhood, we have that for all P bar contained in 0 to T, I keep messing this up, this is open, 0 to T, and some P between 0 and T bar, some fraction of the T bar here, that the following holds. So here's our Taylor series expansion, F of X star plus P bar P is equal to F of X star plus P bar P transpose del F of X star plus 1/2 P bar squared P transpose del squared F of X star plus P, which is less than F of X star. Because this is equal to 0 at the optimal point, and this part we're saying is less than 0 according to our assumption. So this has to be then less than F of X star. And so this gives us a problem once again, that there is some other point that is not the minimizer that is less than the minimizer, contradiction. Therefore, if this is true, where del F of X star is not positive semi-definite, we can demonstrate that X star would not be the minimizer. So it must be the other way around. It must be true that this is positive semi-definite for it to be a, for X star to be a minimizer. So that's first order necessary conditions. Now we can look at the oh, sorry. And if you're wondering, like, where did this come from? Let me just say that really quick. That's also where it says do a Taylor series expansion. It's actually in the right here. So if you're like, well, I don't know how that's a Taylor series expansion, that's actually the same part that they wrote here for Taylor's theorem. So that's what that is from. And it says that this is equal to that for some e in that range. So that's where that part comes from. Okay. So now we're going to look at sufficient conditions. So what is a sufficient condition for optimality? So these are going to be ones that go the other direction. So they're going to be that if certain conditions hold, on the derivatives of f at some point, which I'll call here z star, I think that should say x star. At some point x star, then x star is a local minimizer. So it's going the opposite direction. So before, the necessary conditions said, assume that I have a minimizer, then what's true? And then this one is going to say, I don't know if I have a minimizer, but I know these things are true. Tell me that it's a minimizer. So it goes the other way. So the second order sufficient condition, I will do. I'm not sure if I'll get as far as convexity. I want to give a little time for questions and discussion. So let's do second order sufficient, and then maybe next week we can do directional derivatives and convexity. So here we're going to do second order sufficient conditions. So these ones say, suppose that L squared F is continuous in an open neighborhood of X star, and LF of X star equals 0, and del squared F of X star is positive definite. Notice it doesn't say positive semi-definite here, it says positive definite. Then X star is a strict local minimizer of F. So we can prove this. So it goes like this. So because the Hessian L squared F is continuous and positive definite, at X star, we can choose a radius r greater than 0 so that L squared F of X remains positive definite for all X in an open ball P equals Z such that Z minus X star is less than R. So this is the idea that because del squared F is continuous and it's positive definite, that means there is some range of values for some small amount of points at least, or potentially small radius around this point X star, where del squared F of X must remain positive definite due to the continuous point. So here, this is all the point Z, such that if you take the norm of the difference between Z and X star, it's less than R. So we call that a ball. So taking any non-zero vector P, so say P is non-zero, the norm of P is less than R, then X star plus P is going to be in this ball, because it's, you add a point that the difference, the norm of the difference between the X star and the P will be less than R. And then what you get is, again, using the Taylor's theorem that we wrote above. So here we have this is equal to F of X star plus P transpose LF of X star plus 1/2 P transpose del squared F of Z P is equal to F of X star. So many stray marks. X star plus 1/2 P transpose del squared F Z P, where Z is equal to X star plus PP for some P contained in 0 to 1 open on both sides. And then the way the book finishes is they say since Z is contained in D, then P transpose del squared F of Z P is greater than 0. And therefore, F of X star plus PP is greater than F of X star. And so I mean, a lot of this lecture I just copied word for word out of the book, but this gives the idea of how the proofs are done and the first order and second order sufficient conditions, and now we can have some time to actually talk about it. So let me turn off the